Hi students, today I am going to explain how to determine the resistance of the given galvanometer by half deflection method and the figure of merit of the galvanometer. So to determine resistance and figure of merit, we need a battery eliminator of 2 volt and I need a 2 resistance boxes. So one resistance I can vary up to 10,000, 1000 into 10, I can vary up to 10,000. So I am going to use this resistance box as a series resistance with the galvanometer, and I need 2 keys, and I have a resistance box with a small resistance I can vary up to 100 ohm. So here I am going to use this resistance box as a shunt resistance which is parallel to the galvanometer. So using this apparatus I am going to explain how to determine the resistance of the given galvanometer by half deflection method and the figure of merit of the given galvanometer. So first I will teach you the theory part. So galvanometer working based on the principle of when there is a current carrying coil placed in the external magnetic field, the coil experiences the current dependent torque. So first I will write the expression for the torque. My tau equals to N into I into AB sin theta. So in this case my perpendicular magnetic field, then sin theta is going to be sin 90 and sin theta is going to be 1. So this is the torque. So where N is the number of turns, A is the area of cross section, B is the applied magnetic field. So this is my current. Okay. So the applied current to the coil gets increases, the torque experienced by the coil also gets increases. So if there is a torque, there will be a restoring torque, that is called tau, which is directly proportional to my theta. What is theta? Theta is called your angular deflection. So this is the torque because of the applied current. This is the torque because of the restoring force or the restoring torque from the spring. So I just replace this proportionality symbol by a constant. I can simply write this is going to be some k times theta. This is tau. What is this k? This k is called torsion constant. If I equate these two equations here, then I can simply write k into theta equals to NAB into I. So if you want to find theta, N into AB by k into I. So now N is a constant, so everything inside the bracket is going to be a constant. If my current increases, my theta also gets increases. Current decreases, theta is going to be decreases. Sir, from this I can define 2 quantities. One is current sensitivity, another is the figure of merit. So from this equation I can simply write what is theta, current sensitivity. So I can simply write here current sensitivity. Current sensitivity is nothing but deflection produced by the galvanometer per unit current. Theta by I. This is called current sensitivity. So this is nothing but NAB by K. So N is the number of turns, A is the area, B is the magnetic field, and K is the torsional constant. Actually the torsional constant which tells about the nature of the spring we are using in the galvanometer. Okay. So next I am going to define a quantity is called figure of merit. Sir, what is meant by figure of merit? Figure of merit is nothing but the amount of current required to get one scale deflection. So if I have my galvanometer here, so in the galvanometer we have a divisions from 0 to minus 30, 0 to plus 30. So from 0 to, if I move one division, 0 to 1 division or 0 to 2 division. So what is the amount of current required to move one division in this galvanometer? This is called figure of merit. So the amount of current required to get one scale deflection in the galvanometer is called figure of merit. So just inversion of this, I by theta, the amount of current required to get one scale deflection. So I can simply write this is going to be K by N into A into B. So the SI unit is going to be current ampere by theta division, ampere per division. In this case is going to be divisions per ampere. So my figure of merit is nothing but just inverse of the current sensitivity. So now I am going to explain the circuit part for this experiment. So first I am going to start with, I have my primary circuit. So I am going to connect a cell of EMF E. So I have a battery, key K1. So this is initially connected with the resistance box here. It should be R. This is nothing but my resistance box. It's going to be in generally it's going to be a larger resistance. Okay. So now this is going to be connected with the galvanometer of resistance G. Okay. So now I am going to connect the another resistance here. This is called shunt resistance. Yes, actually this should be a variable resistor with the key K2. So initially for my calculation, so first I am going to explain what is shunt. The shunt, which is the parallel resistor to determine the amount of current flows through the galvanometer. So this is just a conversion of galvanometer to ammeter. Okay, once the shunt is connected, my galvanometer is now act as a ammeter. So first when my K2 is open, this resistance is connected with this. So first I am going to take this here. I forgot to explain, my ES is very much less than the series resistor. Shunt resistance means it is very much less than the resistor we are placing series to the galvanometer. So when my K2 is open, then the current through the galvanometer here only be there, because this is going to be an open circuit, and the current flows through this will be Ig. The same current will flow through this R also. So I can simply write my R Ig equals to total EMF by total resistance. So EMF E by R plus G. So this is Ig. This is my equation 1. So this is I am getting from the, I can calculate my Ig value from this R value and G value, and applied EMF I know from the experiment. Okay, so now I am going to write the current from the deflection, because my current is depending upon the theta. If I know theta value, I can calculate the current. So from this theory part, from the experiment part, I can simply write my Ig, which is directly proportional to the theta. Agree? Ig, which is directly proportional to my theta. So I just replace this proportionality symbol by a constant. Here I am going to use capital K. So Ig equals to some capital K times theta, and then I can simply write Ig by theta equals to K. So this K is called figure of merit. This K, current per unit deflection, is called figure of merit. So I can simply substitute this equation 1 in equation 2. So if I substitute this value here, I can simply write K equals to E by R plus G into 1 by theta. So figure of merit, SI unit ampere per division. So E is, I can calculate, this is applied EMF, R is the series resistance, G is the galvanometer resistance I am going to calculate. So 1 by theta is nothing but what? Theta is the deflection we are getting from the observation. So if I know everything in the right hand side, I can calculate the figure of merit. So then how can I calculate the resistance of the galvanometer? If you want to find the resistance of the galvanometer, we are going to close this. We are going to close this K2. So if I am going to close this K2 here, when K2 is closed, now only this shunt resistance is included with the galvanometer. Now this is parallel with this. So what's happening? The current through the galvanometer, it gets splitted because this is parallel to this. So whatever the potential drop to the galvanometer, that is equal to the potential drop across the shunt. So now the resistance of these two combination will become R prime equals to what? G into S by G plus S. Agree? So now the resistance of this galvanometer as well as shunt resistance is going to be R prime is equal to G into S. G is the galvanometer resistance, S is the shunt resistance. Okay. So from this observation, if I am replacing this here, then I can simply write the galvanometer resistance will be G equals to R into S, R minus S. So this is a generalized formula to find the galvanometer resistance. So this is a generalized formula to find the figure of merit. So if I know R and S value, I can calculate the galvanometer resistance. If I know the galvanometer resistance, if I know my theta from the observation, I can calculate the figure of merit. So now I am going to explain the connections and how to take the readings. So first we are going to do the connections here. So the one wire from the cell to the resistance box, here this is cell from cell to the resistance box, the another wire from the resistance box to the galvanometer, and galvanometer from galvanometer to key, and key to this negative end of the cell. So this circuit is called primary circuit. We finished this first part. So first from positive terminal of the battery to the resistance box, from the resistance box to galvanometer, galvanometer to a key K1, and key K1 to this negative terminal of the cell. So this is called primary circuit. So now we have a shunt resistance connected with a key. So now I am going to connect this shunt resistance which is parallel to the galvanometer. So one end with the one side of the galvanometer and another with the other side of the galvanometer. So first I am going to start with. So this end is connected with here, listen. So this end is connected with the galvanometer. Either way you can connect. So you can connect either this end or this end. And then the another end of the shunt is connected with the key, and this wire is connected with the another end of the galvanometer. So now the connections over. So to take the observation, we need this table. So first we are going to take the reading of the resistance box from this here, and then take the theta from this galvanometer. To get theta by 2, what is the shunt resistance required? We are taking observation of this res from the shunt resistance, and then we can do a calculation for the galvanometer resistance and the figure of merit. So first what we are going to do here, when the key K2 is open, when the key K2 is open, there is no shunt is not connected to the galvanometer. So now is the open circuit. So first I am going to switch on this battery eliminator here. So now this resistance is 0. When this resistance is 0, because everything is going to be in 0, when this resistance is 0, so observe here, the galvanometer current will be maximum, because when there is this 0 resistance, the current through the galvanometer is maximum. Okay. So when we are increasing this resistance, we can control this current through the galvanometer. For example, if I increase this resistance here, this is 1000 into 1, 1000, 1000 into 2. No, this resistance is not sufficient to control the current here. Then next, 1000 into 3, 1000 into 4. So if I apply 4000 resistance here, the current through the galvanometer gets reduced. Okay. So now I am reducing this value 3000. So this is out of my limit. Okay. This is more than 30 out of my limit. So what I am going to do here, I am going to vary, this is already here 1000 into 3. So now 100 into 1. 2, 3, 4. So now listen, 1000 into 3, 3000, 100 into 4, 3400. Here the galvanometer shows deflection of 30. So now I am taking this reading here. When the resistance is 3400 ohm, the theta value is 30. So to get half deflection, this should be 15. What should be my shunt resistance? I have to calculate. So first, now what we are going to do here, we are going to connect this key here. If I connect this key here, what's happening? Now the shunt is connected to the galvanometer. Now the shunt is connected to the galvanometer. So now my galvanometer shows 0 current. Why this goes 0 current? Because the entire current passes through the shunt, which means the shunt resistance is less than the galvanometer resistance. There is no current flows through the galvanometer. So now what we are going to do here, we are going to increase the shunt resistance. So I am going to increase my shunt resistance 10, 20. Listen here, there is an increase in the galvanometer current reading. If I increase the shunt resistance, some current flows through the galvanometer. So now furtherly I am increasing 30, 40, 50, 60, 70, 80, 90, 100 ohm. So here my shunt is 10 into 10, 100 ohm resistance, but my galvanometer shows only 14 deflection, but I need what? 15 for half deflection. So I am going to increase my shunt resistance further. See, now this is also 10, 100, 1 into 10, 100. Now the shunt resistance will be 110 ohm. Listen, the galvanometer shows 15. So in previously, before shunt connected, it shows 30. Now it's 15. So the deflection will be half. To get half deflection, we need 110 ohm resistance in the S. So now what we are going to do here, we are going to remove this plug. We are not going to alter any shunt value. So now the galvanometer again goes to 30. Okay. So now what we are going to do, we are going to adjust this series resistor to reduce the deflection of the galvanometer by 28. Okay. Try to take the reading here. Deflection theta should be even number. Then it's easy to get the value of half deflection, the whole number. So now I am increasing 100, 3500, 3600. Listen, 1000 into 3, 3000, 100 into 7, 3700. Here galvanometer reading is 28. Okay. So 3700 ohm for R, galvanometer reading is 28. So now the theta by 2 is going to be 14. What should be the resistance of the shunt? We are going to calculate. So if I connect this key K2 here, see, listen, I am not altering any value in the shunt resistance. It gives 14 ohm half deflection. So I am not altering anything in this shunt resistance. I am just place the key here. I am getting half deflection. So when you get 14 divisions, I need the same shunt. Now I am going to remove this key here. Then I am going to increase my resistance. Listen, so 1000 into 3, 100 into 10, 1000, totally 4000. Here my galvanometer reading is 26. So again I am writing the reading for 4000. This is going to be 26. Okay, and then if I connect this here for the half deflection, if I connect this key K2 here, which means the shunt is connected to the galvanometer. Observe here, without any change, I am not even touch the shunt resistance. The current is deviated, split at 2. Okay, one part is flows to the galvanometer, another part is flows to the shunt. Now the reading shows 13. So now I can simply write for 13. Again I am getting what? 110. So once the shunt value is fixed, there is no need of changing your shunt value. Okay, so whatever the change in my R value, for the half deflection, I am not need to change the shunt value. So using this R and S value, we can calculate this G. So using this R and S value, we can calculate G equal to R into S by R minus S. If I substituting these two value here, so first G equal to 3400 into corresponding shunt 110 divided by R minus S, 3400 minus 110. So we will get 113.67. So here if I substitute this R value, corresponding shunt resistance, we will get this result. For this R value and this shunt value, we will get this result. So approximately the G value is 113 ohm. Okay, so using this G value and R value, applied EMF is E equals to 2 volt. So if I substituting 2 volt here and this R value here and corresponding G value here, and then 1 by theta, theta is 30 here, for this case is 30, for second case is 28, for third case is 26. If I substituting, I am getting the value of 1.89 into 10 power minus 5 ampere per division. So our second case 1.87 into 10 power minus 5 ampere per division. For this case 1.8 into 10 power minus 5 ampere per division. So if we take the average here, is approximately 1.88 into 10 power minus 5 ampere per division. So this is the figure of merit of the given galvanometer. So using the half deflection method, we can calculate the galvanometer resistance as well as the figure of merit. So figure of merit is nothing but the amount of current required to get the one scale deflection of the galvanometer. So if you like this video, share it with your friends and subscribe to our channel to get the more updates. Thank you.